So hello, everyone. Very glad you could join us this afternoon for our Antarctica Week Festival. This is the fifth of our talks, so we're halfway through the week, and I hope that some of you have come back for several talks, and some of you might be joining us for the first time. So today we've got Britney Schmidt from Georgia Tech in the US who's joining us. So it's morning for her, afternoon for us in the UK. She's a co-investigator on the MELT project for the International Thwaites Glacier collaboration, and the principal investigator of the Iceman team. So I'm sure she'll explain a lot better than I can, but Iceman is an autonomous underwater vehicle, which is designed to take under ice oceanographic data, as well as bathymetry and sonar and imaging of the seafloor. As with all the rest of our talks, she will talk for about 30 minutes, give us a good presentation, and then we'll take questions afterwards. There's a Q&A function at the bottom of your screen, so just type your questions there and let us know where you're from, and if you've got a school that you'd like us to give us a shout out to, we can try and do that along with your question. We've had some that also came in through registration, and we'll try and get through as many as possible. So we'll just move on to you, Britney.
All right. Well, thanks everyone for being here. I'm so excited to be able to talk to you today. Happy Antarctica Day yesterday and Antarctica Week this week. Antarctica is my favorite place on the world, an incredible place. I feel so lucky to have gotten to go. And much like all of you, I'm living here at my house. Our original plan was to be back in Antarctica working with our colleagues in New Zealand on a very similar project to the one that I'm going to describe today, but I'm happy to participate and try to help keep everybody safe by staying at home. So hopefully this is a break from the day for those of you out there. So thanks so much for coming, and excited to answer questions and talk to you all about this. So I'm going to tell you about robots in Antarctica, but first we might as well talk a little bit about Antarctica. You've probably come to know Antarctica as this shape. But it's really about the size of the United States, which is where I live. So it's a pretty big continent, and it's covered in ice, of course. That's what we all know it for. But what you maybe can't quite see here is exactly how deep that ice is. And so the ice on Antarctica can be anywhere from, a few meters thick if it's sea ice, so, a few times my height thick, all the way to about 5,000 times that height. So 5,000 meters maybe at the thickest. So it's an incredibly important amount of ice as well. As you know from having tea at your house or hot chocolate, probably don't put ice cubes in hot chocolate, but the story, right? Is that if you put ice in warm water, it tends to melt. And really that's the story of why we've been exploring Antarctica, particularly through this Thwaites Glacier collaboration who's hosting Antarctica Week. So that's the project that I'm going to tell you about. And I wanted to just kind of orient us. So this is the continent. These are all of the kind of white mass here is the grounded ice. And then there's these big lobes of floating ice that are kind of in this area. And we'll talk a little bit about those in a little bit here. Something else you probably have already heard about Antarctica. This is probably also what you picture when you think about Antarctica. You think about storms and crazy wind. This is from our camp last year out on Thwaites Glacier. So you can see the snow blowing pretty quickly, burying our tent. That took us an entire day to dig out. The experience is something like this. You can just see your work growing for you from the edge of your tent, because all of those big mounds of snow get dug out. It's a pretty incredible place. But there's something else about it that we don't always get to see as humans. And that's really the story of our talk today, which is what's underneath all that ice. So there's a whole world underneath the ice that is just absolutely magical. This is a shot from our down camera on Iceman, which is our underwater robot. And this is just some of the life that's living on the seafloor under ice, very little to no light in the area that this image was taken. And yet we have a whole world of organisms living down there. And so it's not just our climate or our environment that's being impacted by Antarctica, but all of these guys here, and their home is changing too. So that's part of what we're doing with Iceman. So now I'm going to tell you a bit about Iceman, and I'm very happy and very proud of Iceman, and it's been a work done by our group, and our group really is a lot of young scientists and engineers. So Iceman is a robot that we built in my lab. It was a crazy idea that I had before I even became a college professor. So that was terrifyingly long ago, but actually not that long ago. So in 2012 or so, I started thinking about what we needed in order to be able to do better exploration of Antarctica. And I'd already been down there twice, and I had some ideas for how we might change how we were exploring it. And that's kind of where Iceman came from. But it wouldn't have happened without 10 or more undergrads working very closely with us, but over 50 undergrads, so 50 college students at least, participated in some part of the design here. Our graduate students participated as well. We even had some high school students. So this is a thing that kind of all of us can really do. And so this is our vehicle that we built in-house, really to try to answer some of these questions about Antarctica. And you can notice that relative to maybe other underwater vehicles you've seen, if you know Boaty McBoatface, for instance, it's kind of a big, huge robot. Iceman is actually relatively thin. So it's about 3.5 to 4 meters long. So the interesting thing about that is we have to go long and very, very thin. So it's only about 24 centimeters wide, or about this wide. And the reason for that is because we have to fit through very, very small holes through hundreds of meters of ice. So the size of the Empire State Building, or 2 Empire State Buildings in the case of this last year. So we have to go through these really small holes, and that's why we built Iceman this way. So what do we have on there? So Iceman's job isn't just to get down there and take pictures, but it's also to tell us what's going on underneath the ice. So up front, we have sensors that allow us to measure how warm the water is, and basically how much melting is going on. We do that by measuring how much oxygen is in the water, by how salty the water is, and the temperature of the water. We also have cameras. We actually have 2 sets of cameras on top and on bottom that allow the vehicle to see what the ice is. So we take live video. And then we also have sonar that allows us to kind of map the shape of the ice. And that helps us to understand the ice as well. We also have 2 other modules here. So this is kind of showing, sorry, I should have introduced this. So on top, this is Iceman with its jacket on. This yellow material helps it float, because the rest of the material that's kind of shown here in gray is aluminum, so it's kind of heavy. So this stuff helps it float. This stuff keeps it strong, so it can go really deep in the ocean. But then here we can flip each of these science packages out. So we can measure using sonar what the shape of the seafloor is, or we can look for what organisms are in the water column, or how much energy there is, things that they could eat. So we can try to understand what they're doing under the ice. All of the electronics that was built in our lab is in this part of the vehicle. In the back part, we can tell how fast the water column is and also navigate the vehicle. So these sensors here help us know how fast we're going and in what direction. And in the back, we also have an altimeter that kind of measures the ceiling. So if we have sensors that are measuring the seafloor and sensors that are measuring the ice column, and that allows us to tell just how much water there is, and how the shape of the ice and the seafloor work underneath the ice. And then, of course, how do we get moving around? We've got turns and tilts. So these are our directional thrusters here and here, so the front and the back, and they allow us to pivot the robot, tilt it, move around like that. And then in the back, we have our forward and back, our ability to go zooming through the water. So it's really pretty neat. And so the first time that we took this robot down to Antarctica, we took a test version really early, but we really rebuilt it. And you can see here in this next slide, I'll show you the team that's helped rebuild it, and really build the real versions that we're using now. So the first time we took it down was in 2017. And over the last couple of years, We've put over 175 hours under the ice. We've flown 41 missions. We've done 85 kilometers of surveys underneath the ice. So pretty much a lot of work done by this group of people. So here in this picture are both part of our team on Iceman. Those are the folks here. So you can see Dan is waving, Justin, Anthony, there's me in the middle, Andy's right beside Iceman, and then Peter and Enrica and Ben and Matt, who's our lead engineer. Matt started as a college undergrad and is now in charge of the whole engineering side of the robot. And so it's a really cool story of kind of homegrown group of people working on how to explore Antarctica. And so really proud, and we keep students involved along the whole time, and it's been a way for me to learn a lot as well. The other folks that are here are our colleagues from the British Antarctic Survey and from New York University who are on the MELT project. And this was us in McMurdo Station last season. Actually, around this time, just a little bit before this time last year. And it was their first time, the British Antarctic Survey guys and the New York University team, it was their first time ever using Iceman. So we were teaching them how to use Iceman. And here we're standing on the sea ice, which is that thinner ice that we can melt through and kind of swim around underneath. So our team was helping them to understand what operations with an underwater vehicle look like. And it's funny because, you know, every time you go to Antarctica, you learn something new. And so there are people in this picture who've been in Antarctica for the last 30 years, and it was new for them. And I learned new things, and I've been there 7 times. So it was kind of an amazing experience to work between the 2 countries and work very, very closely together. So here's Iceman doing her job underneath the sea ice. You can tell it's sea ice because you can see light coming through the ice. When we get to Thwaites Glacier, which is where we spend our time with the British Antarctic Survey this last season for ITGC, you can't see anything because you have hundreds of meters of ice on top of you, and there's no light. But it's nice to kind of see the robot doing the work that she does from underneath the ice. So back to this picture from the beginning of the talk. So this is back to this Antarctic scene and the way that we're always used to seeing it. But let's zoom in on the places that we know and love so dearly. So we've done most of our work. So as I mentioned, this is my 7th season in Antarctica, and almost all of that work has been done actually at McMurdo, which is the United States base. So it's in West Antarctica. We get there by flying from New Zealand. So we fly from the United States to New Zealand, then we get some gear there, and then we fly all the way down. You might have noticed on that picture of Iceman that it comes apart into 7 pieces. And that's actually partially because we put it in supersized suitcases and we check it onto the plane. So we actually can take Iceman with us everywhere. And that's part of the design for that vehicle. So that's McMurdo. This big, huge flat piece here is the Ross Ice Shelf. So it's about the size of France, and it's a huge ice shelf that we've been doing some work with the New Zealand program. And half of our team in that earlier picture went out with another Iceman out to the back of this glacier to understand it as well. But the place I'm going to talk to you about that we explored is Thwaites Glacier. And so Thwaites is in a very special place of Antarctica. And if you can see, there's kind of this divot here. So it's in this place where warm water is actually moving around the continent, and it's being pushed up onto and underneath the Thwaites Glacier that's kind of sitting out over here. And the important part about it is that everything behind it basically depends on the glacier staying there. So as that glacier gets melted, the ice behind it can start running towards the ocean. And that's why we're so interested and so concerned about Thwaites Glacier, is that it pushes back all of this ice behind it. So let's keep going here. But let's zoom in on this place that we worked last year. And if you look really closely, you can see lots and lots of details. But I think most important to notice are all of these icebergs. And you can see these long fractures and rifts that are forming across the ice. So this is the actual tongue that's left of the glacier. But the glacier is also flowing down here and coming around across here. And so we were over in this region exploring exploring an area that we called Butterfly, that was in the more stable area. And it's not that it's the only place we wanted to explore, but it's the only place that was safe enough for us to go. So even if you're not an expert in Antarctica, you can take a look at what used to be a totally solid sheet of ice and notice that that's not what this ice shelf is. It's falling apart, right? Those are all icebergs. It used to be a solid sheet of ice, and now it's kind of all falling apart. And that's why we're so worried. And so this is a picture of us actually, of the ice as we actually flew over the surface of Thwaites on our way to camp. So you can really see at every scale that there's these big fractures going through it. And we've noticed over the last 20 years with satellite data that the front of the glacier and the tongue of the glacier has been collapsing and moving back. So I mentioned a little bit why that's happening. This is a diagram of basically the scene here. So this, if you want to take a look at this these red lines here, these red lines basically show where warm water is going. And so the story here is that there's fractures that are starting to happen across the ice shelf, and they're picking up because the ice shelf is thinning out, but it's thinning because it's both melting here and melting back at this very special place called the grounding zone. The grounding zone is a place where the glacier, so a big thick sheet of ice, flows off the continent and hits the water. And so then the seafloor comes up to meet it. And right at that point is called the grounding zone. And it's basically where all the action gets started, where all the melting starts to happen. And the faster you melt at this point, at the grounding zone, the more unstable that ice sheet can become. And then it starts moving all of the ice behind it into the ocean. And that's why we're worried. That's why we talk about sea level rise. And that's why it's so important to actually get to these places and make measurements of how fast it's happening. Because we can take pictures with satellites and tell that it is happening, but we can't tell exactly why or exactly how. And so projects like ITGC are important because they let us go there and actually make the measurements. Sounds easy, maybe. Maybe not so easy. This is how we had to get there. So we took big, comfortable planes to New Zealand. We took big military planes to get down to Antarctica. But then we took very, very, very small planes. This is a British Antarctic Survey Twin Otter. So it's a twin prop plane, and it's one of the workhorses in Antarctica. These really small planes allow us to get there. So this is me, our electrical engineer, Dan, and Kaya and Lizzie, who are seismologists or earth scientists that study the geology and the ice using explosions, basically. If you made the talk yesterday by Sridhar, he described exactly the methods those guys are using. So we're crammed in here with all of Iceman's luggage and a bunch of cardboard that we use to make floors so that we don't sink into the snow. So we cram ourselves in there. Luckily, Ollie and our camera person Gemma were able to fly us out there and get us out there safe. Here's our view of camp as we're coming in. Looks like a little town, but it's really just about 15 tents. So not a whole lot going on. Flying in, and this is where we spent 5 weeks living out on the ice and trying to understand what's happening at Thwaites. One of my favorite parts about this entire experience is not only just having the chance to work with great students at Georgia Tech and with our colleagues, but it's just how much you get to work really closely with really wonderful people. And so this is our team that was out at the glacier. So the British Antarctic Survey, NYU, now Penn State as well, and then our team from Georgia Tech and 2 members of the BBC right here. So wonderful group of people. You can see here, this is the frame that Iceman launches off of. And this is the frame that the hot water drill uses. And that's how we get underneath the ice. Wanted to show you a little bit about what it's like to be at camp, because this time last year we were at camp. So this is the Kind of Great British American Bake Off, the Antarctica edition. I thought I might just share with you what Christmas in Antarctica was like for us last year. You can see our decorations. We've got storage containers with a platform over it. That was our table. We've got camp chairs inside the main tent. We're cooking back here on Coleman stoves, but we had a nice fancy night, even decorated just a little bit. I made bread pudding for the first time ever, which is kind of an American favorite. So some of our cranberry bread that we made in our little bread makers and added it together. So I was pretty happy, and that was a fun experience. So I made the bread pudding, and one of our British colleagues made the custard that went on top. It was delightful. So little pieces of home. We also shared in our various cultures. So here we're sharing with our British colleagues an American Christmas tradition of watching Die Hard. And then in this, you can probably see the classic British film in the background. So I love Love Actually. So that was our other Christmas movie that we all watched together in the tent. As you can see, things are a little bit different. Sometimes you just go with whatever. The really good bread came from the camp that had really nice facilities. These are the kinds of things that we're able to accomplish in the field, but it keeps us eating. And then I spent a lot of time while we were working in the tents just eating food out of bags. So pretty exciting there as well. Wanted to just give a little bit of a highlight for the seismic work that our team was doing. So we were digging down into the ice and the snow and burying these seismic detectors, setting off really small explosions and being able to understand the thickness of the ice to help with the whole picture. So we're not the only scientists out there working. I love this picture. This is a picture of Pete, and you can see that big yellow container there is full of snow. That snow didn't get there on its own. We spent an entire day digging out something like 10,000 gallons of snow in order to fill this up and melt it down, because this becomes how we get through the ice shell. So it's not all play. We don't just make bread pudding in the tent, but we're digging snow all day for various reasons, for science, and then also for our access. So that whole bunch of snow there gets melted with those heaters in the background. You can kind of see the heaters in the background of this picture. And our colleagues at the British Antarctic Survey, Keith and Paul, were kind of the team that led the drilling. And so we melt all this snow down, and it creates we create warm water. And then you take basically a fancy fire hose, if you want to think about it. So this long metal piece here is the drill head. And really what it's doing is it's spraying hot water at high pressures. And so it's boring a hole through the ice shelf, and it helps save a lot of energy. It would take a lot of energy to drill through it. So ice melts, so it's a pretty easy way of drilling. So think about that every time you see a fire hose going past you, is that we use them in a kind of a special way when we get to Antarctica. So you can see the long tube here and this metal end. So the folks starting to drill the hole. Meanwhile, we're getting Iceman stuff ready. So this is what our base station looks like. Here's Dan. So we've got a bunch of computers because we are watching live video. We're driving the vehicle. We can do some basic automated motions with Iceman, but it's when we go to these new places that we have never seen before, it's much safer for the vehicle for us to drive it. So these computers show us feeds from the vehicle and show us all the science sensors. This helps us capture the data, and we can monitor what's going on in the vehicle the whole time that we're under the ice. And we're doing these missions for 6 or 8 hours. So they're pretty long missions, and there's a couple hours of setup and a couple hours of takedown every time. So it is a long haul when we do this. So here's me and Andy putting Iceman down through the ice. This is actually kind of a getting started. So you can see it's hanging here off of a strength termination, and it's dangling over a 600-meter deep hole in the ice down through the ocean below. And that's where we're about to send it. So pretty exciting and pretty tense. Here's an example of what it looks like to be driving Iceman. So normally someone else would be driving, but as I mentioned, this year we had 2 teams and 2 robots go to 2 different places. So I had to learn how to drive the robot, which was terrifying, but really fun. Luckily I had Dan there to help me and to monitor all the sensors. So this is the view from Iceman looking down the hole for the first time. So this is the forward top camera, the forward bottom camera, and then this is the view back for the tail, because we also have a backup camera, because everybody needs a backup camera, right? And this is a picture of us driving all the way to the grounding zone, that point I mentioned, that place where the ice meets the seafloor. That's us driving with a PlayStation controller, so something you might also recognize. So, and then on this computer screen is the sonar. This is at the end of our sets of missions, so we were pretty tired and pretty proud of ourselves for making it through that. So just the three of us being pretty relieved that our robot came back. This is actually after our first mission, sorry. And then I've also got another picture later about everything else. So what did we see? So I'm going to show you some videos now of some of the cool things that we saw underneath the ice. And I mentioned there's a whole world that we don't ever expect. And what you can see, these little dangling things here are actually are ice anemones. So we didn't expect to see them there, and it wasn't why we were there, but we did get to see them. They're kind of an amazing little species of anemones that instead of burrowing into coral or into the seafloor, they burrow into ice. But the real point of what we were doing was to get back to that really important place that I mentioned. And so when you see this, all of the stuff that you see in the camera view is ice, but you can notice it's got rocks in it. It's got little grains and pebbles falling out of it. And those are really important observations. Let me show you that a little bit again. So when you're watching this, you're actually watching the ice melt. You can see this stream of particles, and that's the ice melting. All of the stuff falling out of the ice here is the ice melting from the warm water. So this is your eyes telling you what the rest of the sensors on the vehicle see, which is that it's melting pretty quickly. And so when we get back there, we take all of those sensors and we can put them together to try to understand what's happening under glaciers like Thwaites, so that we can understand how that impacts the rest of our planet. And so that's been our team's role, is to try to help understand that. Here's our team at the end of our last dive, pretty relieved to be done. We did 5 total missions. It was an absolutely beautiful day. What a great day to finish up. And then I just wanted to kind of share with you, what did we learn? So what do we learn? Unsurprisingly, the water under Thwaites is really warm. The water down there, if it was balanced, it should be about -2 degrees, and instead it's much closer to 2 degrees above zero, which means it's very, very warm. The ice really is melting quickly. In that video, you could see streams of particles coming out as the ice is melting rapidly back. So we could actually measure that in a number of ways, using the cameras, using the sonars, and using our temperature sensors. The hard work is that we're trying to figure out just how much and how quickly. Scientists and engineers all work together. Everyone works on these vehicles and works on a number of different investigations. And what we're trying to do is figure out the details, because we know it's happening. We just need to know how fast, so that we know how to prepare for it, right? And that's kind of where we all come in. So I sent, one of the poll questions was, what kind of education do you need to help with climate change? And really the answer is, you don't need one. You just need to think about it. You need to talk about it. You need to read about it. You need to listen to scientists. And we need to, each of us, help our communities understand and make changes that allow us to preserve our planet. And so it's part of our professional work to get to go down there, right? Engineers, biologists, everyone can work on robots in Antarctica. But more importantly, every person on the planet is able to help with understanding what we do now that we know what's happening there. So I just wanted to share that. And I hope you really enjoy the rest of Antarctica Week. We don't want to end on a somber note. So I'll just end with a couple of pictures, my favorite pictures showing things that humans have never seen before until that minute. So some of the neat things about being in Antarctica is really trying to understand our planet in ways that we haven't thought of before. So I'm certain that people on this call today are going to be the people doing the next step of this. And we need all of us to think about new ways to do that. Because these pictures are the work of whole groups of people. And so with that, I'll just kind of put up the names of everyone who was down in the field last season, and thank everyone for listening. It's been a real pleasure, and I'm happy to answer questions.
Thank you, Brittany. I thought that was fascinating, actually. It was a really good mixture of, explaining your work really clearly, but also giving us a taste of actually, what you do in your downtime and spending time with everyone there. So that's fantastic. What I'll do, actually, if you want to maybe take your slide down, and then we can have some questions, which is great. So we'll dive straight in, shall we?
Sure.
Let's take a couple from that were submitted beforehand, and then I'll move on to ones that were done here. I've got one here from Peter. It says, given the data you collected, ideally how many sites, do you need to drill, and how often would you need to repeat them?
Yeah, that's a really good question. So every glacier is different. So the answer could be we should drill on every glacier and figure out every glacier. That's probably not the right answer, because it takes a lot to do these explorations. But what we need to do is sample a lot of them, and ones of different styles. So actually last season, I kind of hinted at it, but the other part of our team was out there. We have 2 copies of the robot. And so we went out to Thwaites, which took us 1,200 miles from McMurdo. But on the other side of the ice shelf, our other team had another copy of Iceman, and they were exploring a different style of grounding zone. That glacier, called Cam Glacier, is one of the few that's not really moving. And it's not moving because the glaciers around it have been moving faster. And so glaciers can kind of turn on and off depending on a lot of different factors. Now, the ones that we're worried about have been constantly moving and are not going to stop. But there's other systems that haven't quite been reached by a lot of this warming yet, and then are affected by different dynamics. And we have to understand all of those examples so that we don't overestimate or underestimate what we're looking at. So I think we have a really good understanding now of at least 2 places. But even across Thwaites, not everything is the same. We were in kind of a special area because it was a safer area that we could get to. We'd really like to get closer to the action to be able to know really what's happening in those regions too. So we've done a total of 3 glaciers now of these grounding zones. And so hopefully, a handful more would really help us understand a lot more.
Okay, I have one here. It says, is there a workable recovery plan if the robot gets stuck underneath the ice somewhere?
Funny you should mention that. So the Iceman is on a long tether, so you could probably see that tail coming out behind it. I didn't really talk about it much, but that tether connects us to the robot. And so we have plans to not get stuck in the first place, and we do have some plans to be able to get it unstuck. At the end of the day, that fiber, if we had to, could be cut because you wouldn't want to risk the rest of the science or the safety of any of the team or any of that. But it's also really strong. It's much stronger than any of us could pull. It's rated to about 1,200 pounds, and the vehicle is only about 200 pounds itself. And there's no way that I could pull more than that. So we can't really break that tether very easily. But what having communications in real time allows us to do is, even though the vehicle can kind of keep itself flat and can kind of do some automatic movements, because we're watching, we can help it get in and out, or hopefully not get it into and get out of tight places. And so we've had things like getting the tether wrapped around things, which is actually one of the scariest things. Is if you get the tether stuck, there's not a whole lot you can do about that, except to try to drive the robot back and get it unstuck. So we've done that successfully a bunch of times. Luckily, that didn't happen for us at Thwaites or really at Cam. But that's happened to us in other situations. And so our plan is to remain calm and to think about it. We usually operate with 6 people. So there's engineers, there's scientists, there's logistics people. And I wanted to tell a quick story about that. Was that this last season, we actually got stuck going down the hole on other equipment that was off to the side that we'd all pulled up and made sure it was out of the hole. And it happened on both teams. And so it's terrifying, and it's a really scary time for everybody because, our whole research team has worked on those vehicles, and you don't want to get it stuck, and it hasn't done its job yet. But we just sat there and we worked on it for a couple of hours, got it untangled, figured out how to pull it up safely. And it wasn't as big a deal as we thought it was, but we went really, really slow to make sure that there wasn't going to be a bigger problem. So that's kind of the biggest thing. Our biggest plan is to be smart and to work together.
Probably a huge relief when you actually did manage to hunt.
Oh my gosh. Yes.
Okay. I've got one here from Ben who said, is it pure, well, we would say aluminum, or an alloy?
That's a really good question. I'm not sure the exact composition of this stuff. It's pretty pure aluminum or aluminium. There's a lot of different materials that you could make these robots out of. For what we're doing, this material is strong enough and light. And we want it to be light because every pound you have to put on a plane costs fuel to get to Antarctica. That's why we made it so small. Most vehicles that have this many science sensors weigh about 2,000 pounds, and our vehicle weighs 200 pounds, comes apart into a bunch of pieces. So that's part of it, is we wanted to find something lightweight. If we want to go to deeper, really, really deep depths, so this one can go to about 1,500 meters. If we go much deeper, we either have to get really heavy or we have to move to titanium, which has better properties, can be lighter. It's not lighter, but it's stronger per weight, depending on which one you use.
And I've got somebody here, Paula, who's from Chile, so welcome to her.
Oh, nice.
Yeah. And she's talking about, you mentioning the idea of Iceman being on your mind before you're a professor, and whether you pictured yourself being involved with robotics when you're already knowledgeable in a different field. And so she said, did it happen to you and your group that a fieldwork season didn't work the way you expected? So
yeah, so those are a couple of really good questions. So actually, so my background, so I put that question in there about what schooling do you need to work on robots? And the answer is really any schooling. There are people who work in business who will use data from underwater vehicles, who will use people in business, so you can really work on robots with any degree. My background is actually, I'm a planetary scientist by training. So I am relatively newer to Earth science in the last, 10 years or so, at least as a field. And so I didn't ever really think of myself as doing robotics initially, but I learned, I cut my teeth on spacecraft. So I've always been involved in spacecraft that are exploring other planets. And I was obsessed with submarines the entire time I was a kid. I love the movie Red October, those kinds of things. So I think I'd always had this really big interest in it, been kind of obsessed with marine biology, even though it wasn't my field. And so it eventually kind of came together. And my professional work before then was really focusing on the ocean planets of the outer solar system. And so we want to explore them with robots like this one day. And that was what got me interested in Antarctica. And then I got down to Antarctica for the first time 10 years ago as a postdoc, and was just never really looked back. I was just inspired by the place. And so that's what it took. And what it took was getting down there and saying, what's something that I can bring to this field that no one else is really doing, or isn't doing it the way that I would like to. And then you have to propose it, and you have to eventually see if your colleagues agree that it's a good idea. And luckily, it seems we had a good idea. So that's kind of the story of how I got involved. And I think that most of my team, it's the same way. My students have come from a whole bunch of different backgrounds. Most of us have never thought about Antarctica as a career when we were kids. There are plenty of people who did, but just not necessarily our group. And our group has Canadians and Italians and people from every background and from across the United States. So it's a whole bunch of different people. And then you ask about if we've ever had something go unexpectedly. Oh, absolutely. One of the things that you can always count on in Antarctica is that it never does what you want it to do. It has its own opinion about whether you should leave on time, whether you should get where you're going at all. We had a season where we were supposed to meet colleagues in the middle of the Ross Ice Shelf for it was going to be our first major project through the ice shelf in really deep ice. And we sat in McMurdo, and the fog was so bad over the ice shelf that we never got out there. So we missed our entire experiment out there. And it was just heartbreaking because we'd been down there and we'd worked for weeks near McMurdo to get working. And then we never made it out there. The planes couldn't land. And that's working in Antarctica for you. Other things that happen when you decide that, to use these non-traditional or newer methods, like building an entire robot, it's not like a car, right? And the first cars weren't very reliable. So, you're learning as you go, hey, we think this should all work together. And then you put it all together and you try it out and it does work. But they're incredibly complicated systems. So we had to learn how to balance power and how to, how to navigate better. In fact, this last year, it was finally, we did really well at navigating, but it's a hard problem. It's a really hard problem to know where you are under the ice. No GPS, no one's ever been there before. All the ice kind of looks like ice. So you don't really exactly know which direction you're pointed in. So we've had to figure out how to do that. So there's a lot of ways that it can go that way, but you just work through it.
Before I just go to the next question, I just had someone who was asking actually whether they can get a copy of this presentation. So I just want to remind everyone that all of the talks this week are recorded and they're on the thwaites-glacier.org website, and you can get a recording then to be able to show other people and other students if you want to another time. So I've got another question here. It says, to what temperature is the water heated that goes through the hose to create the hole when you're drilling?
Oh, that is a good question. I actually don't know the answer to that. So if you're interested, I'll bet, well, if you're on Twitter, there is a Twitter account for our British Antarctic colleagues that Pete Davis runs. It's Hot Water on Ice. So they would be able to answer you the exact question. It's not super, super warm. It just has to be able to be high pressure and warm, but it's not boiling, but it's pretty warm. So, but I don't know the actual temperature. Sorry for that.
That's right. But following on from that, Craig's asking how long it takes to actually drill a site. So you mentioned the 600 meter deeps, but how long would it take to drill that?
Yeah. So the exact number of hours, it was somewhere around 26 or so, as I recall. So it was really a pretty amazing effort by Paul and by Pete. So Paul Anker is the lead lead drilling engineer. And so actually the 5 weeks that we were out there, part of that was just getting the ice, getting the whole system unburied, taken out, because it had been winterized. It had been living in Antarctica, under snow and very cold temperatures, getting it built. So actually that was the longest part of the whole thing, is getting all the stuff that's had to be, traversed across Antarctica and then put away for the winter, bringing it back out and getting it working. So that part took, probably 4 weeks or so. And then at the end, the drilling itself goes fairly quickly, and you can't really stop once you start going. So it's a long day, and so they just kind of drilled straight through.
Sorry, I was just going through. There were so many questions, just try and sort of filter through and find some new questions. Well, I can always find new questions, but it's like Catherine, who's at in North Carolina, wants to know how long it took to build the robot.
Oh yeah, well, we started building, we built the first version of Iceman in 2014, and then that basically taught us all the things we did wrong. So we rebuilt it in 2017. So I've been working on the design, the ideas for it. So kind of depends on what you count as how long it takes. One of the hardest things for our team is that we also, we built a new one in 2017, and we built most of that in about 4 months, which is pretty fast. But most people have an entire year to work, right? And we really don't. We have the amount of time left when you subtract that you're in the field for, maybe we're in the field for 3 or 4 months, right? So there's 4 months gone. Takes you about a month or maybe 2 months to ship stuff down, and then maybe 2 months to get it back. So that doesn't leave you a whole lot of months to actually work on the robots. So it's one of the challenges that our team faces, is that when we find something new, we have to kind of rebuild and reformat, and we have to do that relatively quickly. So the first one, that 2017 vehicle worked. It was great. We were really, really proud of it, and an all-student team did that. And well, all students and me, they were teaching me how to solder things, and you know, I have a more theoretical understanding of a lot of this stuff. So it's an all team effort when the PI is also in there trying to help wire things. But it's kind of a neat experience too. So there are things on this robot that everybody's welded, from high school interns to me. And so now we've kind of got a stable platform. So now what we're doing is we're doing things like just tweaking it, making it a little bit better. We're making new instruments for it. Andy, who you saw kind of helping put the robot down, he was the person outside, poor guy. What a champ. He was outside the whole time during the missions, monitoring the tether. And he's amazing at it. But Andy is an electrical and a civil engineer, and he's really fascinated by actually building microscopes. So he kind of does biology with his electrical engineering. And so he's building a microscope for it. And Ben, who is down there, he's building a CTD, a new way to measure the temperature and the salt in the water column. And so that's kind of what we're focused on now. So the pieces, we just kind of continually do new stuff. And then we're building our own software system. So Anthony, who's our lead software engineer, and the team have been slowly building new modules and new pieces of it. So everything on the vehicle will have kind of been built and rebuilt over the last few years.
Okay. So I guess when you're sort of continuing more building and rebuilding, a couple of people have asked, how do you keep the robots from freezing, and how the gears don't freeze, and if they have any cooling system?
Yeah, no, actually, so funnily enough, the bigger problem for these vehicles is how to get rid of the heat. So inside, so the sensors, the main part of the vehicle is actually flooded. So all of the sensors are rated to those temperatures. And the biggest thing that we have to do is not get it filled with water beforehand and then let it freeze right before we go down, because it can freeze. And you can see, you probably saw the pictures with the icicles actually growing off the robot. So most of the equipment is okay to freeze. It doesn't love it. No electronics love to be frozen. But actually one of the hard things is that when you have this pressure bottle, so all of our electronics that Dan's designed are inside this pressure bottle that Matt designed. And so it's really challenging to get the heat out, because all those batteries and all the electronics inside are building up heat, just like your computer does over time. So we actually have to engineer ways to deliver heat to the outside edge of the vehicle in order to get it to cool off, to make sure that we don't overheat when we're on missions.
Moving on slightly from robots, I've got a question here from Damien, who says students at MS 118 in the Bronx are studying metabolism, and they'd like to know how your metabolism changes when you're working on the glacier and living on your tent.
Oh my gosh, you get hungry all the time, for sure. So it's a pretty amazing place. So you're basically never quite your right temperature, because all of the gear that you're wearing, your big puffy jackets, that can overheat you. So you have to layer up, right? So we have to like shed layers, but then it's cold outside. And so you feel better, but you're still actually losing a lot of energy to the outer environment. And so the amount of food you have to eat to just maintain yourself is pretty key. In fact, it's one of the things that we're taught as part of our safety precautions, is to kind of keep an eye on our colleagues, because what'll happen is you'll be working and not notice that your body is losing energy faster than you can really replace it in a lot of conditions. And so if you're not thinking about eating, you might not even be hungry yet. And so that can become a problem. So we start looking for things like the umbles, is what we call them, mumbles, stumbles, and bumbles. So mistakes that people are making because they haven't been eating enough, and their body's starting to get cold or starting to be not optimized. So yeah, so an example of that is that we all kind of have favorite snacks that we bring to the field, and everyone's are a little bit different. I'm a dried fruit person. I have Justin famously loves fig Newtons, so we just kind of have bunches of random stuff that you would never eat. Like I don't eat cookies at my house normally, but I'm just Chips Ahoy or going down. I drink a lot of Gatorade when I'm there. Let's see. So in Antarctica or in McMurdo, when you're kind of planning for the deep field, you can roughly plan on 1 chocolate bar per person per day as a normal thing. Like, can you imagine if you ate 1 chocolate bar per day on a normal, on a normal basis? Like, that wouldn't be a good idea. It wouldn't be a healthy move, but that's kind of one of the things you have to do. And it really depends on what you're doing. So there's some roles where you're not doing a whole lot. And so it's very important not to then eat all of that stuff. But then there's times where you got to pack the calories on.
Sure. Okay, we've got a question here from William. It says, have you picked any pebbles, water, or pieces of ice from underneath the glacier? So you can determine how old the ice or rock is from there.
Yeah, so we don't directly do that ourselves. So, and then on the Thwaites project, we were really interested in the ocean, in the ocean temperatures and how it's affecting the ice. So it wasn't really a focus of that, but there's another part of the project, so that was melt. But we were also working with our colleague James, who's on the Thor project, Thor, I think. Yes. And they were collecting cores. So that same hole that's a long tube that Iceman was going down, it's not the only instrument. So Pete Davis and the British Antarctic Survey guys were putting down CTDs that measure the ocean temperature, and they're measuring the current speeds and measuring turbulence. And those instruments are still there. We put down a mooring after we were done with all of the Iceman deployments and the other instrument deployments, and we left it there so that we're getting a constant record of how things are changing. But as I mentioned, James' project was to collect sediment cores. So rather than picking up individual rocks, what they do is they actually kind of slam this long metal tube down into the seafloor and grab up some of the sediment that comes up. And so they'll be able to do a lot of understanding how the sediment evolved, how the rock underneath it evolved, basically how long that's been ice covered and when it was uncovered is kind of the idea. And we're comparing those cores across the entirety of Antarctica. So another example of, and biologists will work on those cores probably to see what's in there as well. And so we're not collecting individual rocks, but it's an idea that we've had. In terms of the age of the ice, that is actually done a different way. So there are other places in Antarctica where they take really long ice cores. And then what you can actually do is you can map the layers in the ice back to where the ice core was taken using ice penetrating radar. So you take a radargram through the ice and you can see the annual layers that have accumulated over time. And you can trace those back to the core so you can say the age of the ice that you're actually looking at. And we have estimations of it, of course, just based on how deep the ice is, but it changes from place to place. So you kind of tie it to those ice cores.
Okay. So this comes back slightly to when you were talking about having tense moments, and someone was talking about bearing in mind the length of ice fin and the depth of the slim hole that it has to go to. How do you angle it to bring it back up?
Yeah, that is something that we've worried about a whole lot. So the nice thing about ice fin, though, is that it's kind of like a pendulum. That's a little bit terrifying when it's windy out and the ice fin is not in the hole yet, because it feels like it's going to swing around a little bit. But when it's in the water, it's floating neutral. So that yellow jacket on the outside of the aluminum frame allows it to just float perfectly neutral, which means that if you like tip it, or you just kind of bop it on the nose or bop it on the tail, the whole robot will tip over, and then it'll go back to righting itself. So the nice thing is that we actually kind of have a system on the back of the tail that we basically do that. We take the tether, we get the robot back to where the hole is, and then we kind of tip it up and it pops it like this and it shoots back up the hole. And we've tested it 1 million times. So we did what we call dead robot tests to make sure that we didn't have to do it. So we can help it if it's hard, if we got stuck or something, we can get the robot to tilt down using the thrusters and we can drive it. But if something happened and the communications were lost or the batteries died or something like that, we'd have to be able to get back in the hole without that. And so we've done tests after tests after tests after tests of how to get that done. So, and that was something that we worked on really hard while we were still in the field. This is one of those things where like everyone always asks you, well, didn't you test this before you got there? And we're like, of course we tested this. We tested this every day, 100 different times, but we couldn't test getting back through 600 meters of ice because we just don't have 600 meters of ice. So it's kind of a funny thing. So you have to think your way through the project or through the problem and then go test it in a safer place. So we go to the sea ice outside McMurdo, and we were testing this all the time. We first started it in a big hole where we could have gone down, or we couldn't have gone down, but we would have been able to pull the robot back through the hole really easily if it didn't work. And then we started using it on different size holes so that we could actually get to what we knew we were going to have in the field. So.
Okay. And Elaine's asked, how might you be able to use a future model of Iceman on another planet, no less?
Yeah.
What technology needs to be improved for that to happen?
Yeah, so that's kind of the fun thing about working on these places is that this is our planet, but it's pretty alien, right? Like it's a pretty incredible place. And so one of the things that our original funding actually for this. So this last year we were working with grants from NSF and from NERC, and those were the folks giving us the money to go down to Antarctica. And when those grants happen, they're paying salaries for students, they're paying for students to go to grad school, they're paying for parts of the robot, they're paying for the airplane flights, all that kind of stuff. But the reason that Iceman got built was actually through NASA. So we proposed this idea. Oh, and actually through Georgia Tech. Georgia Tech gave me some seed money early on when I was an early professor to help build the first one. So we built the first one with that money. It wasn't a whole lot of money, which is why it wasn't very good. And then we rebuilt it once we got a grant funded, but we proved that we could do it. And so then NASA gave us money to build Iceman as a test bed. And so one of the things that we have to do is we have to figure out how would you navigate? And that's one of the things we're working on. So we're using computer vision and different learning on the vehicle. And so that's one of the things that data, in addition to the climate change data, we're also using that to try to figure out how you use, okay, when everything's white and bumpy, how do you know which white bumpy thing you just passed? How do you do that? And I mentioned all the instruments. Andy's microscope is the kind of microscope that we expect would be used on any number of missions to outer space. Microscopes are really useful for various different things, so we're trying to do that. We have an entire group of the same engineering and science team. We all work together on all these projects. We're doing a mission study to study a melt probe where you kind of would combine the hot water drill, not exactly, but it would be a melt nose on a vehicle like Iceman that would be taking samples as it's going through the ice until it gets to the ocean. And then we're using Iceman also to just test out different types of instrumentation and different ways of thinking about it. Part of what we have to do before we go to another planet is learn how to think. And so most of our experience on Mars, for instance, is pretty normal human experience in a weird way, right? It's a different planet, but if you got to the surface of Mars, you'd know what to do, right? It's rocks, okay. I kind of know what that looks like. That's a mountain, whatever, I can drive around. You can imagine what the rovers can do to simulate what you would do. Well, how do you get to an ocean that's under kilometers of ice and know what to do when you get there if you haven't asked those questions here first? So there's this kind of hand-in-hand thing. So what we've been doing is, while Iceman itself is not the version of the robot that would go one day, it is pieces of that, and it's the thought process behind it that is really important, because it's teaching us what we don't know. And humility is a big part of exploration. It's something that I think needs to be talked about a lot more, because we tend to think of, super cool dude, hike to first place, stand on mountain. That's not really how it works. That's how people don't come back from the exploration, right? The way that you do this well is you sit and you think and you work with good people and you work as a team. And so that's what we're trying to do, is we're trying to teach ourselves all the things we don't know, so that maybe when we do get there, we can do a better job. So it's not really an answer exactly, but it'll have some kind of a melt thing on the front of it, be powered a little bit differently, but conceptually it's very similar to the same things we're trying to do in Antarctica.
Fantastic. I think we've reached our hour, actually, Brittany, already. So I know, I'm sorry we couldn't get through all the questions. There are just so many questions that come through all the time. So, but thank you everyone for joining us. Remember, we've still got another 5 more talks for the rest of the week. So, you're welcome to come to any more of the others. And everything will be available as recordings on the website as well. But thank you very much, Britney.
Yeah, thank you, everyone. I'm sorry we couldn't answer all the questions, but yeah, feel free to, if you're a Facebook or a Twitter person, if you look for Iceman Robot, you'll find us, and you can kind of follow along with what Iceman's doing and learn more about stuff. There's lots of details there, and of course, keep an eye on the ITGC program and the return to the field, hopefully in a big way next year. Let's cross our fingers. So stay safe, everybody.